Hey, I guess that's one way to enter a room. That happened for the first time last night, and I don't know how to change the setting. I think it's a new Zoom thing. And it also happens when I enter breakout rooms. So very awkward, way to enter. So, welcome to class. Good to see you. Please come in, make yourself seen. That's much appreciated all around. And we'll get started in just a second. I think it makes sense to have Stata up and running. So have that ready. What else? We're going to talk about the Sexer and Furman reading on crisis bargaining and nuclear blackmail. So you want to have your notes from that reading or the reading itself open. We're going to watch a short film clip on statistical inference, and we will then do an exercise or kind of an example of univariate hypothesis testing together. And since we don't have a ton of folks here, I know some of our Wednesday people attended last night, and so that was kind of populated to a greater number, but maybe we'll just do, instead of doing it in breakout groups like I did yesterday, we'll just all do it together right here in this main room. So good. Everybody should have received an email from me a few days ago on Sunday, I believe it was. I will continue to try to lay out just some things to keep in mind midweek by email, so that way you can have some communication from me about what you should be thinking about or working on, or any messages I want to send, or any notes about prioritizing certain things, or just other things that I want to bring to your attention midway through the week, since we're only seeing each other on a weekly basis. So do continue to look out for those email messages. If you received that, in an email address that you would prefer not to receive it at, please just let me know that in the chat or by email what your preferred email address is. I get a roster from the registrar, and it has a column called preferred email, and that's the one I've been using. But I think especially if you're a recent, if you've recently matriculated into SIS or registered, then I might have an email address that isn't your preferred one. So generally speaking, I have your AU email address, but for some of you, I have like a Gmail address or Yahoo or something else. So if you're getting those emails somewhere where you'd rather not get them, just let me know your preferred email address. Okay, good. We're going to jump into content here in just a second, but before we do that, what questions do you have in terms of the course? Anything in that email that causes confusion, concern, or interest, let me know, because I'd rather tackle administrative and logistical matters right here at the outset. We'll have time later to discuss problem set 1. We'll do a Q&A on that. We'll have time later to discuss cross-tabulation, which is something that you learned about for today. And so we can dive into those things later, but just, are there any administrative or logistical matters that you want to raise at this point in terms of, how things are working, where to find certain materials? I think you probably have a pretty good grasp on that so far. Anything at all? Okay, so then I'll just remind you of the preface at the top of the email, right? Because you read all the bullet points, right? You get the gist of what the different handouts were I mentioned. a couple of important points that I put in the discussion forum about do files for the problem set, which I can show you in person if that would be helpful later, as well as another one about setting your command directory. But the thing at the top of the email, I just want to highlight, and I know you all are doing the work and you're putting in the time and the effort so far, but I do just want to remind you that, you have signed up for a pretty significant undertaking in your first 7 weeks of summer. Typically, right, during a normal semester, one class means 2.5 hours of class time and 5 hours of out of class time on average, right, for work. And sometimes it might be a little more than that, sometimes a little less, but that's how it should average out over the term. And of course, for this class, it's our 2.5 hour class meeting, plus another 2.5 hour kind of course content in terms of the lectures that I post for you for, let's say, a Friday or Saturday session. And that usually comes in below 2.5 hours. But I also know I've given you a starting with Stata tutorial in a 3-part series. So, all of that's part of like secondary course content. But then in addition to that, right, you should be expecting to put in an extra 10 hours on average just on the class weekly. And maybe you're coming in a bit ahead of that right now, maybe a little bit below, I'm not sure, but averaged over the course of these 7 weeks, right, it's essentially 5 hours of course content plus 10 hours of work outside. And so make sure, I know we have work and internships and personal things and maybe travels or things like that, but just make sure that you continue to prioritize this class in terms of the time and effort it requires. And I think that given the pace, so far. If you have any questions or concerns about that, come talk to me in office hours, and I'm happy to, to talk with you about working more efficiently or dealing with, the timing of assignments or whatever it is that I can do to help. Okay, great. Final call for any just thoughts, administrative or broader observations. Yeah, Camille.
Not really administrative, but I just want to you went up this briefly when class first started, but like, what is your expectation? Like me personally, I took stats, like college stats in high school, and I took stats again like my freshman year of college, and that was like 5, 6 years ago. So what is like your expectation for us overall, especially for those who haven't had consistent math over the past couple of years?
I would like to say my expectation is excellence. Commensurate with being an SIS graduate student. Sometimes people meet expectations, surpass expectations, or underperform expectations, right? And at the end of the day, that's why we have assessments in the class in terms of problem sets and exam and final project. But that's my kind of bar for an A. But I think there's various ways to kind of demonstrate that. And I think, let me just put it this way. That is my desire. My expectation is strong performance. Maybe, some folks aren't, quite at what I would consider to be excellence, but, strong performance. The syllabus lays it out in terms of grades. The one thing I will say that is sometimes surprising to students, I'm not sure why, but it sometimes is, and that is effort is not what I'm assessing, right? I'm assessing your products and the work products that you submit. And so I would just say that effort is generally correlated with the quality of the products that you submit. But you might have some folks who put in less effort, but nonetheless submit excellent products. You might have some people that put in a ton of effort, whose products are maybe not quite at that level, right? But generally speaking, effort is correlated with the quality of final product. So the more effort you put in, the more likely it is that you're going to have a final product that meets those kind of higher bars of, being good or solid or excellent or, well executed or whatever kind of adjective that we would want to put on it. So I simply don't grade or assess on effort alone, but generally speaking, the more effort you put in, the better, the better the outcome is going to be. Um, but I will let you know as we go along, how you're doing based on primarily the problem sets, right? I mean, that's going to be your indicator of how you're doing. And that's why the problem sets are worth a substantial portion of your grade when you aggregate them together. But it's also why they're not such an enormous part of your grade, like the entirety of it, that you can't have a bad problem set or two or a mediocre problem set or two and still, not recover in the form of a final project or the exam. Right. And so actually I'm glad you asked this question because that leads me to one more observation about the problem sets, given that you're working on the first one now. Um, I see the problem sets as serving two purposes. One, and I would say the lesser purpose, is to assess your learning so far, right? That's important. But in terms of the actual like placing a grade, so I can put it down in my Excel sheet and it will, of course, factor into the final grade in the class, to my mind, that's the less important thing, right? The more important thing about assessment is I can see where people are going right and where people are going wrong, and I can try to intervene or calibrate, based on that. The second purpose of the problem sets is as a pedagogical or learning tool. And that's the one that I think is much more important. I can talk to you all day long about statistical inference or about using stata and interpreting your results. I can give you tutorials. You can watch the videos of me demonstrating different examples. But my experience when I've gone through, 8, 9, however many classes I took throughout graduate school in quantitative analysis, what really made it sink in for me, no matter how many times I heard it, was to actually be forced to do it, and to work through problems where it was like, here's the question, and you need to figure out not only what the answer is, but what the means to that answer is, right? What's the pathway that I need to take in order to get to that answer? And so you see that the problems, the practice problems, I give you the answers that you can consult. And in practice problems one, I even kind of tell you, click here, type this, right? In future practice problems, I'll do a little less of that. I'll still give you the answers, but I'll do a little less of the hand holding. So that way it's something closer to a problem set, but you still, have the answers along the way. But it's in the problem sets where, you really have to say, okay, I've learned through the starting with stata tutorials as well as the lectures about, um, about, let's say, cross tabulation, like for today, um, what that means, how to do it in stata, and how to interpret the results. And you need to be able to read a question, right? That is, and I don't hide what it is that you're supposed to do, but you should be able to read a question and kind of figure out, based on what I've learned in the starting with stata tutorials and also in the lectures, the substantive lectures, which of those things do I need to apply, right? And so I would have, if you can, a printed copy, if possible, of at least the starting with stata tutorial handouts. Because to really boil it down, I think what you're trying to do in the problem sets is to look at each question and figure out, if you think about the tutorial handouts as a menu, right? Which thing do I need to choose from that menu to apply to this question to get the answer? And so that's really what you're after. And that's kind of an easier way to go about it. Somebody I talked to in office hours called it kind of like a cheat sheet, the starting with Tata tutorial handout. To some extent it is, it's, here are the commands. And generally speaking, although there's one caveat I need to make later when we talk about the problem set more, generally speaking, there will never be something on the problem set that you have not been introduced to in the starting with stata tutorials, or now going forward in the substantive lectures about different methods and tests. So I know that was a super long-winded answer to your question, but it raised a lot of, I think, really good things. So thank you for that. Any follow-ups on that or anything else come to mind? Okay, very good. So what I would like to do is just jump ahead here in a video, and I just want to show you this this video. Jot down some notes, just thoughts and observations. This isn't something you'll necessarily be tested on or anything like that, but I think this will reinforce in some ways what it is that you did for class 4 about statistical inference, hypothesis testing, what a p-value is, what confidence intervals are, why we put a lot of credence into those things, but also some of the pitfalls of putting too much emphasis on things like p-values and statistical significance. So I'll probably show this to you in two iterations, let's say, or in two parts. And I'll stop it partway through just to collect some of your insights and thoughts. Okay, let's start here. And I will share. Okay.
Science, the ultimate test of our understanding is our ability to make accurate predictions. On a grand scale, scientific theories like Einstein's general theory of relativity have to make predictions that can be tested to become accepted. In that case, it took 4 years before a full solar eclipse revealed that light passing near the sun curved, just as predicted by Einstein's theory. The first proof he was right that the sun's mass distorts the fabric of space-time, what we experience as gravity. In fact, the scientific method demands a hypothesis which leads to a prediction of results from a carefully designed experiment that will test its claim. Surprisingly, it wasn't until the 1920s and 30s that a British scientist, Ronald A. Fisher, laid out guidelines for designing experiments, using statistics and probability as a way of judging results. As an example, he told the story of a lady who claimed to taste the difference between milk poured into her tea and tea poured into her milk. Fisher considered ways to test that. What if he presented her with just 1 cup to identify?
If she got it right one time, you'd probably, well, yeah, but she had a 50-50 chance just by guessing of getting it right. So you'd be pretty unconvinced that she has a skill.
Fisher proposed that a reasonable test of her ability would be 8 cups, 4 with milk into tea, 4 with tea into milk, each presented randomly. The lady then had to separate them back into the 2 groups. Why 8? Because that produced 70 possible combinations of the cups, but only 1 with them separated correctly. If she got it right, that wouldn't prove she had a special ability. But Fisher could conclude, if she was just guessing, it was an extremely unlikely result, a probability of just 1.4%. Thanks mainly to Fisher, that idea became enshrined in experimental science as the p-value, p for probability. If you assume your results were just due to chance, that what you were testing had no effect, what's the probability you would see those results or something even more rare?
If you assume that there's a process that is completely random and you find that it's pretty unlikely to get your data, then you might be suspicious that something is happening. You might conclude, in fact, that it's not a random process, that this is interesting to look at what else might be going on, and it passes some kind of sniff test.
Fisher also suggested a benchmark. Only experimental results where the p-value was under 0.05, a probability of less than 5%, were worth a second look. In other words, if you assume your results were just due to chance, you'd see them less than 1 time out of 20. Not very likely. He called those results statistically significant.
Statistically significant. Now, this is a terrible word. It could be quite insignificant. You could be detecting a very, very, very small effect, but it would be called, in the mathematical lingo, significant.
Since Fisher's day, p-values have been used as a convenient yardstick for success by many, including most scientific journals. Since they prefer to publish successes, and getting published is critical to career advancement, the temptation to massage and manipulate experimental data into a good p-value is enormous. There's even a name for it: p-hacking.
P-hacking is when researchers consciously or unconsciously guide their data analysis to get the results that they want. And since 0.05 is kind of the bar for being able to publish and call something real and get all your grant money, it's usually guiding the results so that you arrive at that P of 0.05.
How much p-hacking really goes on is hard to know. What may be more important is to remember what was originally intended by a p-value.
The p-value was always meant to be a detective, not a judge. If you do an experiment and find a result that is statistically significant, that is telling you that is an interesting place to look and research and understand further what's going on. Not, don't study this anymore because the matter is settled.
In a sense, a low p-value is an invitation to reproduce the experiment, to help validate the result. But that doesn't always happen. In fact, there are few career incentives for it. Journals and funders prefer novel research. There is no Nobel Prize for replication. Another solution to p-hacking and the overemphasis on p-values may simply be greater transparency.
More and more, what people are doing is publishing their data. And so it's becoming harder and harder to lie with statistics because people will just probe and say, well, give me the set you analyzed and let me see how you got this result.
Statistics continues to play a fundamental role in science, but really anywhere data is collected, you'll find statisticians are at work, looking for patterns, drawing conclusions, and often making predictions.
Let's pause there for just a second. Let's take, two observations, questions, thoughts based on what we've just seen, right? There were a number of things covered there, right? About data, p-values, uncertainty, margins of error. So, what did you take away? Jacob?
So what I liked is when he mentioned that the p-value was meant to be a detective, not a judge. So you still have to it shows you what kind of the evidence, what it looks like, and then you kind of have to decide a bit. And also something else, as someone who has like an educational background in STEM, when they were talking about experiments and how they want them to be successful, for anyone who does like more experiments like qualitative research, there will be times where there's a lot more failures than successes, from what I can tell, at least with novel research and stuff. And so if anyone gets discouraged, failure is pretty common.
Yeah, and especially if I can just add to that, I think that was an excellent point. And just to add to it, it's especially common when people are abiding by the proper processes for data collection and analysis. And one of the things that they flagged in there was that there's an incentive structure built into research and scholarship to find statistically significant results. And there's been a lot of pushback against this more recently as people have I think become more humble maybe about quantitative analysis, what it can tell us, but also what it can't tell us. But for some time, and I think there's still some remnants of this, you have some analysts, scholars, researchers, and others who are doing what they can to get statistical significance, to get p-values low enough so that way in their studies they can put the little asterisk next to their variable, right, their cause, to say that it's significant, right? And as the interviewee in there said, it's a terrible phrase, statistically significant, because it seems to suggest in a very qualitative way that what you have found, right, is important. But that's not necessarily the case. And we're going to see this much more when we talk about regression analysis, where it's possible to have a statistically significant relationship that is almost meaningless in terms of the impact that it has. And so let me just say, without going into it for another week or two, that again, it is possible to have statistical significance, which is a measure of our confidence in a relationship between two variables, but not have substantive significance, where that X variable actually affects that Y variable in any meaningful way, right? It could be absolutely minuscule, right? And so for example, if you have, well, I'm always thinking about time management for the class. Let's just take for one example, and if this confuses more than it clarifies, we'll talk about this more, in a week or so. But imagine, right, we have a ton of data about whether baseball players use Visine before the game or don't. We might find that systematically there is a relationship that those who put Visine in their eyes before the game have a higher batting average than when they don't use Visine before the game, right? Maybe, right, we see that there's a correlation between those two things and that we have enough evidence to support the hypothesis that using Visine before the game increases one's batting average, right? The number of times the player gets a hit per times that they come up to the plate for an attempt. It's possible that we see enough data and evidence to support that conclusion, and therefore it's statistically significant, right? There's evidence that gives us confidence of an effect of Visine on batting average. But the player's batting average goes up on average by one additional hit for every 1,000 times they come up to bat. Right? In other words, we get an additional 0.001 on their batting average, for those of you who know baseball. And if you don't, though, you still get my point, I think, right? That we may detect a relationship between two variables, but as the person in the interviewee said, it could be a very, very, very minuscule substantive impact, because statistical significance is a measure of our confidence, right? Our certainty versus uncertainty, that there's a relationship between two things. But it doesn't measure how much of a relationship there is, right? How big of an impact the cause has on the effect, right? Certainly, if you compare putting Visine in your eyes before the game versus putting steroids in your arm before the game, right? The impact is going to be different between those two things. The Visine impact might be like this, whereas the steroid impact is more like this. And what I'm trying to tell you is that statistical significance doesn't tell us the size of the impact, tiny versus large. All it tells us is how confident we can be in rejecting the null hypothesis. And that's why time and again, right, they said in here that we're really asking ourselves, how likely is it that we would observe the results that we got, or those that are more extreme, under the assumption of the null hypothesis? In other words, if we assume that the null hypothesis is true, and then we collect a whole bunch of data and evidence, how likely is it that we should then, you know, how likely is it that we would have amassed the amount of evidence that we did if the null hypothesis was correct? And so I think when I talked about this in the lecture, I put it in terms of like guilt versus innocence, right? If we assume that somebody is innocent of a crime going into the court case, right? That is like our null hypothesis. It's the assumption of innocence until we prove guilt. Then, right, it's the job of the prosecutor to amass a bunch of evidence. And then the question before the jury is, how likely is it that we would have this evidence if the person was indeed innocent? You know? So it's like the O.J. Simpson trial or whatever other trial you can think of, right? We assume they're innocent walking in the door. But then you say, okay, the bloody glove, the white Bronco, the knife at the scene, the et cetera, et cetera. How likely is it that we would have this evidence, right, of this amount and magnitude if the assumption of innocence was correct? If that amount of evidence is, great, then we overturn our assumption of innocence. We overturn the null hypothesis. If that amount of evidence is not so great, right, then we stick with the null hypothesis, the assumption of innocence. So it really depends on how much evidence we have. And the evidence, of course, comes from empirical observations through systematically collected data, right? And so we're going to talk more mechanically about that or mathematically about that in a few minutes when we talk about the Z-score. I will shut up. Is there another observation, though, that we can take before we hit play again? What's something else that you noticed from this video? Or a thought or question? Melissa?
Yeah, I thought it was important that she said that I think it was near the end, how important it is to share the data you have, because I think that's relevant to both quantitative and qualitative. Recently, on the qualitative side, he had like cobbled together things that weren't actually accurate. And when people finally actually looked into what this person had researched, they realized that it was done under extreme bias and some of his sources didn't make any sense. And so it put into question a lot of his academic work focused on that particular country. So I mean,
absolutely. In fact, so you find this across the social sciences. Psychology has undergone a crisis where a lot of studies have not been able to be replicated now that they're sharing their data more and more. A replication crisis. And so I think, a lot of chickens are coming home to roost a little bit, where you can identify studies that were doing what they described as p-hacking, kind of manipulating their tests or data or certain analytical procedures, right? Or omitting certain cases or observations so that way they could obtain statistically significant p-values. But going back to Jacob's point from before, I also, I concur that it's important to think about statistical significance and p-values below 0.05 as being indicators of something that we should study more, right? That we have come across a hypothesis that holds for the data in this sample and based on the methods that were used in this particular study. But one study does not the truth make, right? And so this is why we really need an aggregation of studies that are all about the same research question and put forward the same hypothesis, but maybe study it in different ways with different data or with different methodological techniques, drawing on different samples. So that way we get a propensity of evidence pointing in one direction or another, or we can see the extent to which there's actually a debate. This is why people say, look, the jury is out when it comes to, climate change. It's like 99.5% of studies or something like that point in the direction of all of the elements of, anthropogenic climate change being, human exacerbated and coming through global warming via depletion of the ozone, right? All the steps in this causal process. But there are other, there are other hypotheses that have more mixed results, and we still need more research to understand maybe whether they hold, right? Whether these hypotheses bear out based on evidence, number one, or what I think is really interesting is when and where do these hypotheses apply, right? So it becomes less about, is there some universal law or theorem or truth about some relationship between two things, but maybe the when and where of that question that's more interesting, right? Or under what conditions does this hypothesis hold versus not? And so that's where we find a lot of our, I think, progress in knowledge. Okay, fantastic. So let's go ahead and just watch a few more minutes. This will bring things into the American political realm, and then we will move on.
Though they don't always work out. The presidential election of 2016 was a tough one for pollsters, the folks who conduct and analyze opinion polls. Hillary Clinton was the overwhelming favorite to beat Donald Trump right up to Election Day.
Trump is headed for a historic defeat. He's going to lose by a landslide.
I think that she's going to have a very good night.
The New York Times put Trump's chances at 15%. One pollster on election night gave him 1%.
A projection of a 99% chance of winning, is that correct?
The odds are overwhelming of a Hillary Clinton victory on Tuesday. I would be very surprised if anything else happened.
And of course, Trump won, and Clinton lost.
People were repeatedly told Hillary Clinton is the candidate most likely to win this election, and she didn't. And I think that really left people feeling almost lied to, almost cheated by these numbers.
So what was going on with the polls? And exactly how do people predict elections? One way is just by asking people who they'll vote for.
One of the great things about polling is that we don't have to talk to everybody in order to find out what the opinions are of everybody. We can actually select something called a sample.
Sampling is a familiar idea. To see if the soup is right, you taste a teaspoon, not the whole pot. To test your blood at the doctor, they typically draw less than an ounce. They don't drain you dry. But in many circumstances, finding a representative sample is harder than it sounds.
Just really quickly, right, note that that is the basis of statistical inference. When I say over and over again, statistical inference, we're talking about drawing general conclusions based on a sample of a broader population or a broader universe, right? And so we're saying something about a much bigger, broader class of events or units or whatever our unit of analysis is. Peace agreements, treaties, protests, civil conflicts, individual voters, elections, political parties, right? Whatever our unit of analysis is about, countries, country years, we are taking a sample from a much bigger pool, a universe of cases that has happened historically, that is currently happening, and even that will happen in the future, which is why sometimes when we talk about explanation, we also talk about prediction, right? Because in some ways we're generalizing to cases that haven't even happened yet. When we make a claim about conflict and the effect of, let's say, the exclusion of ethnic groups from the political process and how that affects the likelihood of civil war, we're basing it on data that we've observed, a sample, but it's not every civil war that has been for all of eternity. Perhaps it's every civil war that is currently ongoing. Usually our data captures that. And it certainly doesn't include civil wars that are yet to be. But our statistical inference, right, the conclusions that we draw are about ethnic exclusion and civil wars writ large, right? All that have happened, all that are happening, and all that will happen, because we're making generalizable claims, statements, and ultimately theories. So what they're describing there is what I mean when I repeat the term statistical inference. Okay.
Let's suppose that this is the population of about 1,000 people in a city. And we want to know, are people for or against converting a park into a dog park? And so these green beads down here are going to represent people who are for it, and the red beads are folks who are against it.
Talithia's first step is to take advantage of an unlikely ally in sampling: randomness.
The beauty of randomization is that as long as you throw everything from your population into one pot and randomly pull it out, you can be sure that you're within a certain percentage points of the actual value that's in that pot.
So the plan is to randomly sample the beads. But how many? That depends on how much accuracy Talithia wants. One measure is the margin of error. The maximum amount the result from the sample can be expected to differ from that of the whole population.
Real quick, I just want to ask you, so what do you think will give you the most accuracy? Right? They just said, how many individuals is she going to draw out to make a sample from the total population? If you have, I think she said 1,000 individuals or something about whether to do the dog park or not do the dog park, it would be resource intensive and onerous and sometimes absolutely impossible to draw a sample of the entire population, right? And so we draw a sample that is a subsample, right? It's a sample beneath the total of the population itself. And he just said that based on the amount of accuracy we want, that's going to affect how many people we sample, how many beads she randomly draws from that jar. What will give us more accuracy and what will give us less accuracy?
More people.
That's right. The more you sample, the more accurate you will be. Now, there's more to that story in terms of how you sample, making sure that it is representative. So we do want it to be random, but we also want to ensure that it's representative. And they'll talk about some of the challenges of that in the American political context in a minute, including, telephone calls and who answers and that kind of thing. But at the end of the day, the more people in your sample, in other words, the larger your N, number of observations, the closer you are to the total population that you're trying to sample, and therefore the more accurate your results, right? Because the more data you have. All right, excellent.
It's the one measure is the margin of error. The maximum amount the result from the sample can be expected to differ from that of the whole population. It's the plus or minus figure, often a percentage, you see in the fine print in polls. But there's also confidence level. Inherently, there is uncertainty that any sample really represents a whole population. The confidence level tells you how sure you can be about your result. A 90% confidence level means, on average, if you ran your poll or sample 100 times, 90 of those times it would be accurate, within the margin of error. Talithia knows the total number of beads is 1,000, and she's settled on a plus or minus 5% margin of error at a 90% confidence level. That means she needs a sample size of at least 214 beads.
Here are the results. We got 103 red beads and 111 green. So about 48% of our population would vote against and about 52% would vote for. Now, remember that margin of error that we talked about, that plus or minus 5%? So once you take that into account, those numbers really aren't that different at all. So I guess you could say this puppy is too close to call.
In fact, within the margin of error,
I like
the
dumb
stats
jokes.
got it right. there were an equal number of red and green beads in the jar. While the sampling error built in from the mathematics can be quantified, there are other errors that can't.
The other parts of the error, how we word our questions, how the respondents feel that day, the responsibility to predict what their behavior is going to be somewhere down the line. All those sources of error are something that we can't calculate.
And there's a catch to random sampling for polls, too. A few decades back, when just about every household had a landline, finding a random sample meant randomly dialing phone numbers.
Into the 1970s and the 1980s, we were getting 90% response rates. If we randomly chose a phone number, somebody on the other end of that phone would pick it up and would do the interview with us.
Those days are over. Thanks to caller ID and answering machines, people often don't answer their landlines anymore, if they even have one. Response rates are way down.
Only about 10% of people respond to polls, so you're kind of crossing your fingers and hoping the people you reach are the same as the ones that are actually going to vote. For example, we found in 2016, pollsters were not reaching enough white voters without college degrees.
If there's a bias in the data, you cannot recover from it, as we've seen from some recent elections.
After Donald Trump's surprise win, many wondered if polling was broken. But if you look at the polls themselves and not the headlines, on average, polls on the national and state level were off by historically typical amounts.
So when I hear people say, oh, the polls were wrong, then it partly reflects people's interpretations about the polls being wrong, where people for various reasons looked at the polls and they said, these numbers prove to me that Clinton's going to win. When we looked at the polls, we said, these numbers certainly make her a favorite, but they point toward an election that's fairly close and quite uncertain, actually.
And in 2016, the U.S. presidential election was just that close. Trump's victory depended on fewer votes than the seating capacity of some college football stadiums, spread across 3 states: Pennsylvania, Wisconsin, and Michigan. And there were some problems with the polls in those states that led to underestimating Trump's support, according to a postmortem by a consortium of pollsters. Nate Silver, the founder of the website 538, is one of the biggest names in polling, even though he doesn't generally conduct polls.
Our job is to take other people's polls and to translate that in terms of a probability, to say basically whether who's ahead, which is usually pretty easy to tell, but then how certain or uncertain is the election is the more difficult part.
Like a meteorologist, Nate presents his predictions as probabilities. On the morning of Election Day 2016, he gave Clinton about a 70% chance of winning, and Trump about a 30% chance. That's like rolling a 10-sided die with 7 sides that are Clinton and 3 that are Trump.
People who make probabilistic forecasts, they're not saying that politics is intrinsically random. They're saying that we have imperfect knowledge of it, and that if you think you can be more certain than that, you're probably fooling yourself based on how accurate polls and other types of political data are.
Ultimately, interpreting a probability depends on the situation. While a 30% chance might seem slim, if you learned the flight you were about to board crashed 3 out of every 10 trips, would you get on the plane?
As this plane only makes it to its destination 7 out of 10 times, please pay attention to our short safety briefing.
Or if a weather forecaster said there's only a 30% chance of rain, and then it rained, would you care?
If it does rain, no one demands to know, why did it rain? We have to get to the bottom of this. We can say, like, it just did. It might have rained, it might not have rained, and as it happened, it did. I do think there's a certain natural resistance to seeing things that maybe we care about more than whether it's going to rain or not, like elections, in that same way.
As 2006.
Okay, we will call it there. There's more to that documentary. And in fact, when I first started showing it in this class, it was not publicly available. And so I grabbed it from PBS and showed it from there. But now it is on YouTube. And I was going to try to grab that for you real quick. And put it in the chat. Here it is. So let me just post it. There we go. And so if you want to watch more of it or you want to review what we watched, you're more than welcome to. We started somewhere near the 20-minute mark. So there you have it. And yes, I just want to say as we start to kind of wrap up on this part of the class, Christine's point is exactly right. You know, rather than results being significant or not, it's more about whether the findings are due to chance or not. And that's why we're ultimately trying to model uncertainty, or we're trying to create a model that takes into consideration the degree of uncertainty we have about a relationship that we've asserted in a hypothesis. And so I think one of the folks that they talked to said, you know, look, politics, or in our case, international affairs, is not random, but we do have uncertain knowledge of it, and we want to try to represent the degree to which we have uncertainty around our explanations and around our predictions. And so that's really what we're doing in our hypothesis tests. We're starting with a null hypothesis. We're collecting evidence. That evidence may point in the direction of rejecting the null hypothesis in favor of the research hypothesis. We do that when the evidence is, let's say, great enough that our p-value is below 0.05, because the p-value is the probability of observing the evidence that we did by chance alone. Right? What is the probability of observing as much evidence as we did purely by chance, right? And so the lower the p-value, the more confidence we have in the alternative hypothesis or the research hypothesis. And therefore, the more confidence we have in rejecting the null hypothesis, that there's no relationship between the variables. Good. So we'll talk more later about the margin of error and confidence intervals, especially when we get into regression analysis. But those were two concepts that came up that I think are important, right? The margin of error represents, you know, the kind of maximum amount that a sample differs from the population from which it's drawn. And so this is why you see in a lot of polls plus or minus 3.1%, right? You know, so many of the polls, when you look at ABC News poll, Fox News poll, whatever it might be, it's plus or minus 3.1. Why? Because 3.1% is the margin of error you get when you poll 1,000 people, right? When the number of observations is 1,000. And so that's why it's a very common thing that we see. The confidence interval is, as they mentioned in the video, a level of confidence that we have in our results. And so a 90% confidence interval that they referenced in the video means that kind of corresponds with a p-value of 0.1. A 95% confidence interval corresponds with a p-value of 0.05. The confidence intervals are related to the p-values that we kind of seek, or that we're using as a you know, kind of a determinant of statistical significance. And so what that means is, I think, just to repeat what I believe they said in the video, I think they used the number 90, right? So that a 90% confidence interval means that 90 samples out of 100, or 9 out of 10, will represent the underlying population from which those samples are drawn within the margin of error. 10 samples out of 100 will not represent the population from which it's drawn within the margin of error. And so this was kind of the preface for them building into this notion that we have uncertainty around our predictions and our explanations of things. Donald Trump's election is a good example of that, right? But I think they explain pretty well in that video where that uncertainty can kind of come from, a variety of sources. And basically our inability to play God and be omniscient and know exactly what, what the answers are to the world's biggest questions. So with that said, why don't we go into the class website, and I want you to open up handout 6, univariate hypothesis test example. And we're going to do this one pretty quick, but I just want to run through an example of a hypothesis test. This is often a little bit harder for people to grasp than bivariate hypothesis tests, like you learned about with crosstabs for today and the chi-squared statistic, and then what we're going to go to over the subsequent days, where we put together an X and a Y, a cause and an effect, right? A variable 1 and a variable 2. And we're seeing if there's a relationship between them and our degree of confidence that there is a relationship and that it's not due to chance alone. We're going to get there, but I think the univariate hypothesis test is an important starting point. And it's all about what we said a few minutes ago was statistical inference, trying to infer something about a broader population or a universe of cases based on a sample that we've collected. And so again, you can think about it as, I think they said, a taste test of your soup with just a spoonful, or taking an ounce of blood and making a determination about whether you have, particular health problems in your entire bloodstream, right? So we're taking a sample and we're trying to say something about the broader population from which it's drawn. So with that said, we're talking here about a pollution example where, we're essentially testing the air to see the degree of pollution that we have. We'll jump into that example, but Leo, what's your question or thought?
Would you say that could be applicable to like the when we talk about the vaccine and how much that is the success rate that they present on the news, and how people perceive those as like and how that affects the confidence on the vaccine? Like there's people who look at like, oh, the Pfizer has a 90% success rate versus the Johnson, who has a probably 80% chance, even though they all do the same thing. But I think that people's confidence on it, depending on the success rate and how that data is presented on the media, that's sort of I guess has an influence on how much people go about getting vaccinated.
Absolutely. So that's a great kind of contemporary example of where studies were conducted to determine the effectiveness rate of the different vaccines. And certainly some vaccines are more effective than others, not only the ones that we typically see in the United States, right, with Pfizer and Moderna and Johnson & Johnson, but you have vaccines rolled out from other countries as well, and other institutions that have different rates of effectiveness. They do that in more of an experimental setup. And we will talk towards the end of the term about, I used to teach it at the beginning, but I've now kind of moved it towards the end to talk about the difference between experiments and experimental approaches to analysis versus observational studies. In short, experiments are much more controlled. Observational studies are those where we let the world unfold as it does. We observe it and collect data on it. An experimental study is one where we actually manipulate the world as it unfolds. And I'll go much more into detail about that another time. But in these experimental studies, for example, you bring in a sample of people who have not yet had, let's say, COVID-19. You give some of them the vaccine, you give some of them a placebo, right? Like salt water or something else. Because you don't want to have some other, potential cause, like a psychosomatic thing or some other, you know, uh, um, potential cause affecting the efficacy or the determination of efficacy. And so there, right, you have a control group and an experimental group. Nobody knows which group they're in actually, right? And so you're doing an experimental manipulation of the world as it unfolds. In other words, who gets this versus who gets that. So there's more researcher intervention in an experimental study compared to an observational one where we just see how things go and we're collecting data based on what we see. But at the end of the day, you're exactly right. We're determining efficacy rates based on a sample, and then we're saying, look, if the efficacy rate is 95%, then we're going to generalize out from that sample that 95 out of 100 people who get this vaccine will not get COVID-19 even if exposed, right? So that, that's exactly what's happening. That's a really nice intervention. Thank you. So with that said, let me just help you move quickly through this example about pollution. So if we look at, I'm just pulling it up here. If we look at handout 6 together, I'm gonna just kind of move you quickly to B. So we're talking about a random sample of 300 readings of a pollutant in the air, right? So our sample size is 300 because we've done 300 readings of how much air pollution there is of a particular pollutant. We got a mean level of that pollution of 1,271 parts per billion, right? That's how many particles there are per billion within our air samples. So it's a mean from those 300 samples, but what we know is that the mean is made up of a whole bunch of different observations. And sometimes those observations are all tightly compacted around the mean. Sometimes the mean, though, is composed of observations that are really spread out, right, around the mean. And that spread, as you know, right, is captured by the standard deviation. I've given you here a sample standard deviation of 150 parts per billion. Now, just remember that the standard deviation, I know it's kind of a new term for a lot of people, but the standard deviation, if you want to think about it in kind of just, basic, how should I grasp this concept terms, the standard deviation is kind of the average difference between the mean and all of the observations that make up that mean. You with me there? Does that make sense? Great. Just to make sure, because I see nodding heads, but I also see a couple of crinkled eyebrows or whatever, right? So let's just say really quickly, if I can, yes, okay, good. Right, let's just say that we have a whole bunch of data points. Right, so these are just observations. I'm kind of spreading them out just so that way we can see them easily, but they're all really, just on one axis because it's one variable, right? Okay, so here's our data points. We might say that the mean is here, right? So this is our sample mean. The standard deviation is the average difference. Let me zoom in here. Right? It's the average difference between the mean and each data point that makes up that mean. right? Some of them are close to the mean, some of them are further from the mean. But the standard deviation tells us, well, what's the average distance or difference between the data points and the mean itself? And so that's how the standard deviation helps us to understand spread. Variance is something that we can't really understand. But when we take the square root of the variance, which gives us the standard deviation, then we have the spread, right, or a representation of the spread in the original units of the variable itself. So if this is parts per billion of pollution, and the standard deviation equals 150, the cool thing about the standard deviation is it represents this spread as the average difference between the mean and all of the data points in parts per billion of pollution, right? So it's in the units of the original variable itself. And so you'll become more comfortable, I think, as you continue to use the standard deviation over the course of the semester, especially if you kind of force yourself to kind of, every time you confront the standard deviation, think about it and what does this mean? And put it back in these terms, right? Average difference. Whoops. Between the mean and the data points that make the mean, right? Every time you see the standard deviation, do that interpretation, think about it, right? In the original units of the variable, you'll become much more familiar with thinking about standard deviations. Okay, fantastic. So if we come back to handout 6, I'll go ahead and let you get started on this, but I've worded some of these a little oddly, so I just want to clarify. Question A is, what is the estimated mean and standard deviation of the population as a whole? Does somebody have an answer to that? What is the estimated mean and standard deviation of the population as a whole? Take a stab. Jasmine?
I might be reading too into it. Is that a trick question or?
It's not meant to be, but I can see how it seems that way, and that's why I wanted to clarify this. So go
Like
ahead.
as a whole, because I'm thinking it's in regards to our sample. So would we say that we don't know, or would we just use what because we're not calculating like our confidence yet? So
Correct, but what were you just going to say? Would we say we don't know, or would we just use?
yeah, but we just use the information that we've pulled from our sample.
Perfect. We would use the information that we have because our best estimate of the population mean is our sample mean. Right? That's the best that we have. For example, if I want to know the GPA of incoming graduate students into the SIS program when they were undergrads, right? I could pick a number at random, or I could take a sample, maybe the sample that's in front of me right now, and I would ask you, what was your undergraduate GPA? I would then calculate the mean and the standard deviation, and I would say that my best guess of the undergraduate GPAs of SIS graduate students is the mean of the sample that I have in front of me. Right? And maybe there's some bias in that sample. Maybe people who take SIS600 in the summer are overachievers, or people who have, more commitments during the regular school year and need to knock some things out in the summer, or what have you. So there may be some sample bias there. But generally speaking, right, you're a representative sample, or a sample that I would feel confident in. It's random. And, within a certain margin of error that is connected to our standard deviation, we have an estimate that is better than a random guess. And that's always our, kind of question. Are we doing any better than just a random guess? And in this case, we certainly would. So with that said, A tells us that our estimated mean is 1271 parts per billion and 150 parts per billion. For question B, what is the estimated mean and standard error? So the estimated mean remains the same, right? Still 1271. Now, though, you're calculating standard error. So go ahead and take a minute. We won't break out into groups. Let's just do this together. What's the standard error? What's the equation for it? And how do you calculate it based on the information we have? And once you think you know, go ahead and just raise your hand. Connor, I'll go to you, but let me give it 2 minutes because I want to see if other people can work their way into it. So remind yourself of the standard error based on your notes. What is it? How do we calculate it? Okay, Connor, tell us what you did.
So the formula is that, so the standard error is the standard deviation of the mean. So of the, yeah. And so the formula is,
it's the standard deviation of the sample, but yes.
Sample, yeah, sorry. So you divide it's now I'm blanking on what the numerator means, but it's the mean. I think it's the mean of the sample divided by the square root of the number of observations in your sample.
Yes, except you had the numerator correct before, right? So in the numerator is the standard deviation. In the denominator is the square root of your sample size. And so here we have the standard deviation of 150, right? And so that represents the spread of data in the numerator. And keep, think about division, right? Or fractions or whatever. When the numerator is larger, the number is bigger, right? When the denominator is larger, the number is smaller, right? So if you think of like 2 over 1 is 2, 3 over 1 is 3, 4 over 1 is 4. So the bigger your numerator gets, the bigger the number gets. 50 over 1 is bigger than all of those. 100 over 1 is bigger than all of those, right? So the bigger your numerator, the bigger the number. The bigger your denominator, the smaller the number, right? 1/2 is bigger than 1/4, is bigger than 1/8, is bigger than 1/16. So as the denominator gets larger, the number is actually smaller. So keep those things in mind. Your standard deviation is the spread of the data around the mean. That's in the numerator. So the bigger the spread around the mean, the bigger the number is getting for the standard error. So the standard error is growing when the standard deviation is growing. You with me there? As the standard deviation, the variance is bigger and bigger and bigger, the standard error gets bigger. In the denominator, we have the square root of our sample size. In this case, it's 300, right? That's our sample. As our sample gets bigger and bigger and bigger, our standard error gets smaller, right? Because as the denominator grows, the standard error gets smaller. That's because the more data we have, we just said this a minute ago, the more data we have, the greater accuracy. So the standard error, which is a measure of our uncertainty, shrinks. Okay, so those are the two main components of our standard error. Excellent. So what does that give us? Did anybody calculate it out? So what is it, Christine?
Are you asking for the square root or just the standard?
I'm asking for the standard error itself.
I got 8.66.
8.66, right? Because it's 150 standard deviation divided by the square root of 300, which is 17.32. So 150 divided by 17.32 is 8.66. So we stick that to the wall and say, okay, our standard error is 8.66. Great, we'll use that later. Okay, now let's move on to C. C says the World Health Organization recommends a standard of 1,250 parts per billion as the maximum level of this pollutant. We don't want more than 1,250. So now what we want to do is determine a z-score. A z-score, as you learned, right, is a statistic that then serves as kind of a means to a p-value, right? We calculate a z-score representing the difference between the sample that we have and some hypothesized value of pollution, right? And so we need to determine what our hypothesis is. And we're going to see, is there a statistically significant difference between our sample mean of pollution and our hypothesized value of pollution? So what do you think our hypothesized value of pollution should be? And we could just pick at random 1,000, 1,500. But is there something that makes more sense? Yeah, Shannon?
Shouldn't it be 1,250?
Because?
Because that's what like the standard is?
That's what the standard is, and we're trying to figure out, are we more polluted than the standard? Right? We're trying to see, is our pollution level more than the standard? Now you might say, well, we already know it is. Right? I mean, we know that our sample mean is 1,271 parts per billion. 1,271 is greater than 1,250. So case closed. The problem, right, is that there's uncertainty around our sample of 1,271. We don't know that our level of pollution is 1,271 parts per billion. We know that it's 1,271 parts per billion with some margin of error, right? With some degree of uncertainty. And we want to know, is that degree of uncertainty so large that it's actually quite possible that our level of pollution is below 1,250, right? I mean, especially if we're thinking in policy terms, that let's say in order to mitigate the pollution and bring it down to a level, you know, that is satisfactory, it's going to cost, you know, $500 million, right? And you have to build new filtration plants, or you have to do regulatory measures that are going to affect, you know, economic prosperity or something like that of industry, and you're going to get pushback from lobbying groups and all this stuff, right? I mean, there are major consequences. And so we want to know, how confident are we that our sample mean of 1,271 is representative of the broader population? In other words, it's representative of all the air. Because if it's not, if we don't have much confidence that it is, then we might need to do more studies to actually see, you know, if we actually are polluted beyond 1,250, or perhaps we're not. So what is the level of confidence? Very good. So to do that, we're going to do a z-score. We're going to obtain a z-score, and we're going to figure out the p-value that's associated with it. So as you know from the z-score, our equation is the observed value which in our case is the observed mean, 1271, minus our hypothesized value, which Shannon just said is 1250. 1271 minus 1250 is 21, right? So that's our numerator. And in the denominator, what do we put for our z-score calculation? Go ahead, Jasmine.
Sorry, I pressed the wrong button.
No worries.
The standard error.
The standard error, and we just calculated the standard error above is 8.66, right? And so now we do 21 divided by 8.66, and we get
2.42.
2.42. So our z statistic is 2.42. Now, let me see if I can open just really quickly. Oh, I linked to it. I forgot. In the instructions, right, I give you a link at the end of question C, right? A z table can be found here. And so this shows us our z table and our associated z-score. Let me share my screen so you all don't have to do this separately. Okay. Get rid of this. Yeah. All right. So what we want to know is, where is our z-score, right, relative to our mean? The z-score could be in negative territory, or it could be in positive territory. And what we're really trying to figure out is how many standard errors is it away from the mean. It can be standard errors in the positive direction or standard errors in the negative direction, depending on the value of our z-score. What we're ultimately measuring is how much space or area under the curve is shaded in gray. Jasmine, go ahead.
Would our z-score not be negative because is it not the hypothesized mean, or is it not the sample mean subtracted from the hypothesized mean? So our z-score would be negative, or no?
It's the observed mean, so the sample mean minus the hypothesized mean. So it would be positive.
Okay.
But that brings me to something where I kind of was kicking myself of using this example, because I didn't introduce you all to the difference between one-tailed tests and two-tailed tests. So that's my mistake. But we'll talk more about that maybe another time when we do t-tests. But let me just say a quick word on that. So we have, let's say, directional versus non-directional hypotheses. And in a non-directional hypothesis, I think I drew a picture of this last night. I just wanted to look and see. Yes. Yeah. Let me see if I can just share this with you. Like this. Are you looking at this screen with a bunch of my drawing on it? Okay, great. So here's our z-score here, right? In the top left, we did the observed mean minus the expected mean divided by the standard error. And the first thing to just remember is that, you know, as I said before, sometimes we think about this stuff as being kind of smoke and mirrors or this kind of mathematical kind of stuff. And I just want to remind you that the z-score is drawn directly from things we directly observed in the world, right? Sample data that we collected from things that we could observe directly. And also from some hypothesis represented by this standard that we don't want to surpass, right? And so if you know that the z-score is composed of real world data and evidence plus some boundary that we don't want to cross, right? And that is what feeds into the z-score. I think it feels a little less like, you know, the heavens opened up and kind of rained down some numbers on us, right? We can actually think that, oh no, this is rooted in real world empirical observations. Now, I got a little sloppy with this as I was drawing, and I'll save the time from trying to draw it again. But you know, you might recall from the lecture that what we want to know is, well, where is the z-score on this line here, right, on the axis, where you might have one standard error here, two standard errors here, three standard errors here, right? And then the same in the negative direction. And really the z-score is kind of how many standard errors away from the mean we are. And so in this case, right, our z-score is 2.42, meaning we're almost 2.5 standard errors in the positive direction. And this entire curve, right, the blue line representing this curve is our probability space, right? Essentially the entire space of our p-value. Our p-value can range from 0 to 1. So, there's some percentage within there. 1 would be 100% of the probability space, everything shaded below the blue line. And what we want to know is, well, how extreme is our z-score in the positive direction or the negative direction? And our z-score, remember, comes from data. So how extreme is it? How big is it in the positive direction or the negative direction? And as we said before, it gets bigger when the difference between our observed mean and our expected mean is bigger, right? The z-score gets larger when the difference between those two things gets larger. So if we had an observed mean of 2,000 parts per billion pollution, and our threshold or standard was 1250, then the difference would be even larger in the numerator, and therefore our z-score would get even bigger, right? In the denominator is our standard error, which captures uncertainty. As the standard error or uncertainty gets bigger and bigger and bigger in the denominator, the z-score gets smaller. As our uncertainty gets smaller, the z-score gets bigger, right? Because it's in the denominator. So the question is, how big is our z-score in the positive or negative direction? In the two tails of this distribution, right, under, let's say, a normal hypothesis test, a non-directional hypothesis test, you would have the upper tail with 0.025 and the lower tail of 0.025, which accounts for 2.5% of the probability space in the upper tail and in the lower tail, right? If it's 0.025 probability space, it's 2.5% out of the 100%. In the top and in the bottom, 2.5%, when you bring it together, makes what? 5%. P equals 0.05. Right? If we allow 2.5% in the upper tail and 2.5% in the lower tail, when you add them together, you have 5% in the tails. And that's the 5% probability space represented by P is 0.05. So that would be our standard hypothesis test. Now, in our example, just to kind of wrap it up, we are doing a one-tailed test, a directional test. Why is that? A one-tailed test asks, well, let's put it this way. A one-tailed test makes a commitment in terms of which direction we are willing to observe our hypothesis. In other words, if we take it to our example, we don't really care at all, and we're not even testing if our pollution level is below 1250 by a certain amount, right? Our pollution level could be 1249, it could be 1,000, it could be 300, it could be 3. It doesn't matter to us, right? We're not testing how low it is beyond a certain threshold. We're testing if we're above a certain standard. And since we're only interested in whether we surpass that standard on the upper end, then we're doing a one-tailed test, what we would also call a directional test. What that means is, instead of putting 0.025 in the top part of the distribution and putting 0.025 in the bottom part, right? 2.5% on either side. We're putting all 5% on the upper tail. And what we want to know is, does our z-score get big enough to be past 0.05 in the upper tail? The last 5% of that upper tail. Does our z-score get into that space or not? If it does, we reject the null hypothesis, meaning that it's highly unlikely that we would have observed a pollution level that we did in our sample if the true pollution level was 1250 or below, right? So again, the p-value is the probability of observing the pollution level that we did in our sample if the true pollution level was 1250, the standard, or less. If that percentage is very, very small, below 0.05, we reject the null hypothesis, and we say that our pollution is too high. It's above the standard. We're very confident. We're more than 95% confident that it's above the 1250 standard. If our z-score doesn't go far enough, right, to leave less than 0.05 in that tail, and it leaves something more than 0.05, maybe it leaves 7% or 10% or 20% in that tail, then it means that we don't have confidence at the 95% level to say that our pollution level of 1271 is actually above the standard 1250. Right? Because there's variation and noise and uncertainty around our 1271 estimate. And so we can't say with confidence that our estimate of 1271 actually represents that the total population or the entire air, right, is above 1250 as the standard. And so we would need to study more to have greater confidence. And maybe if we studied more, we would see that we have too much pollution. Or if we studied more, we would have less error and uncertainty around our results, and maybe our sample mean would be much less. Maybe the next time around when we sample not 300 times, but 1,000 times, our sample mean might be 1249 and we're safe. And we could say, right, with much greater confidence that we're actually polluting at a level below the standard. But, you know, we would need more study to come to that conclusion. So just to wrap things up, our p-value and the way that we find it, just come back to it, if I exit this, comes from this z-table. And I just want to make sure everyone can read the z-table. What we're doing with the upper tailed test, right, is we're saying how much probability space is in this gray area. Remember, our z-score, we want to know how high it is. Is 2.42, right, z equals 2.42, far enough to the right that the amount of space left in the white area is below 0.05. You with me? So our z-score of 2.42, we come down to 2.4, and then we go over 0.02, right? You see it up here, 0.02. So it's 2.4. That gives us in the whole number and the tenths, 2.4. And then across the columns is hundredths. So 2.42, we need to come over to here. And it's 0.9922. 0.9922 is the amount of space in our probability function above that is gray, right? As it says here, it's the amount of space that is to the left of the z-score. But what we just said is we want to know how much space is to the right of the z-score, right? We want to know how much space is white, not gray. So there are two ways we can find the amount of space that's white to the right of our z-score. One is to do 1 minus the gray area, right? If we know this entire area under the curve is 100% or 1, then we simply subtract out the gray area. And the gray area for 2.42 is 0.9922. So if you do 1 minus 0.9922, you get 0.0078. And that's our p-value. The other way to do it, and the way I did it in the solutions, is to just cheat and to go up here and look at the negative. Negative 2.42 is 0.0078. Right? And so maybe this might have been what prompted your question before. I think it was Jasmine, right? About, whether we want the negative z-score. We do want the positive z-score, right? Because we do observed minus hypothesis. But in this case, so we don't have to do 1 minus the p-value for the positive z-score. We can simply look at the other side of the table. Connor, go ahead.
But that only works because we had a directional hypothesis, or does
Correct.
that? Okay.
It only works because we were doing a hypothesis in the positive direction. No, I'm sorry. It only works because we had a positive z-score. So when you have a positive z-score, you're pretty much always doing 1 minus whatever it is, right? And you can just look at the opposite side of the table to determine that.
Okay.
Now, what's that?
We can always do that
Yeah.
if we have a positive z. Okay.
Correct. I'm going to leave it there. I could go a little further, but I'm just going to leave it there. So that's good. I wanted to stop that portion of the class at 7. So we're a little bit later than that, but I more or less on target within a margin of error. Sorry, not sorry. So what I would like to do now is move on to, let me just remind myself quickly. Let's take 5 quick minutes to talk about crisis bargaining and nuclear blackmail. We can take a quick breather after that, and then take any questions that you want for the remainder of class about cross-tabulation, problem set 1, or the content from class 4 and 5, right? From asynchronous and then today's class. So really quickly, and please be primed and ready to answer the basic questions that we'll always ask about empirical articles. What's the research question? What's the dependent variable? How is it measured? What's the independent variable? How is it measured? There are some others, but I think that will do it for what I want to cover with Sexer and Furman, and that should put us back on time. So what are Sexer and Furman asking here? What's their research question? And I know you'll need a minute to pull that up and switch gears here. It's fine. Yeah, Camille?
In layman terms, like basically they're arguing like whether or not nuclear weapons offer any advantages in international crisis bargaining.
Absolutely. Can you put it in? So you said whether or not, which follows what they do, right? Which is kind of a yes or no question. It's like, does having nuclear weapons help bargain against an adversary, or doesn't it?
Yeah.
And so that's great. You've identified, especially there, the variation in the dependent variable, right? The dependent variable is bargaining success. And maybe we can add a concept to that in a minute, but that's essentially it, right? Successful bargaining. How can we put the question in a why or what explains format that focuses on variation in the outcome? We called it successful bargaining. What's another concept or term that represents the dependent variable that they're after? And how can we ask a why or what explains question about it?
And you say use a different word than successful bargaining.
If we can. I just want to hear another concept. I think yours was good. It captures what the article is about. What is it that the challenger is seeking from the target or from their adversary?
The level of compliance.
Right. They want compliance, which represents successful bargaining, right? But they want the adversary to comply with their demands. So we can think about the dependent variable as that. Sometimes a target or an adversary will comply, sometimes they won't, right? So now we have variation in an outcome. What's the research question then in a why or what explains format?
Would it be like, how do nuclear weapons?
Why or what explains? Sorry to interrupt.
Never mind.
Why or what explains? I'm going to be a real asshole about this. Go ahead, Shannon.
Would it be like, what explains compliance in international bargaining?
Okay, what explains compliance in international bargaining? You could throw the word variation in there if you want to, ensure that folks know that you're not just talking about the cases where there's compliance, but you're trying to compare when there's compliance versus when there isn't, right? So what explains variation in compliance in international bargaining? Good. What about a Y version? And let me go one step further. Can we also introduce the unit of analysis in the question as well? Christine?
So for the Y version, could you say, why are some states more compliant than others?
Yes.
Is that just too broad? Because I mean, that would be my assumption, is you introduce that and then you can introduce variables, but it does seem too broad.
I think it's fine. What I would add to it is that second ask I made after you raised your hand, which is, can we introduce in some way like the unit of analysis here? What's the unit of analysis in the study or in the data set? Because what you just said here is, why do some states comply? But we're talking about not just states, but a particular kind of scenario among states where the data set isn't just state by state by state, nor is it what we've used with the state year, which is state years, but it's something else. Shannon?
Would it be something like, what why or what explains variation in compliance among states with nuclear weapons?
No, because we want to make sure that our question doesn't assume that or suggest that we're only looking at states with nuclear weapons, right? So I see what you're doing there. You're trying to introduce the potential cause. And I think that's something you could do with a follow-up how question, right? How does nuclear possession affect the compliance of states in international bargaining or something like that? But if we just stick with our first question, focused on variation in the outcome, which is compliance, how can we bring in the unit of analysis? Jasmine?
What explains, well, they're studying dyads, so what explains successful coercive diplomacy between two nations, I guess between dyads?
Okay, so thank you for bringing the dyads in. Let's try to bring that into the question that was asked before, right? The question that was asked before is, what explains variation in compliance? Or why do some states, I think Christine's was something like, why do some states comply with others' demands or something like that? And so what we might ask, just to kind of wrap this up, is I might ask the questions in this way. Why do some adversaries in militarized disputes, because that's what the unit of analysis is, militarized interstate disputes, based on, as Jasmine just said, dyads, state A, state B, right? So why do some adversaries in militarized interstate disputes comply with a challenger's demands while others don't? Right? Why do we have compliance? Sometimes, but not others. But more concretely, why do some adversaries or targets in militarized interstate disputes, I think adversaries is better, comply with the demands of a challenger while others don't? Or if we want to put it in a what explains format, we might ask, what explains the willingness of a target of a militarized dispute to comply with demands of its challenger? Or what explain, as I think somebody put it even more succinctly before, right? If we take that question, what explains variation in compliance in militarized interstate disputes, right? And I think that captures it well. Okay, so we've covered a lot of ground here. Let's go to the dependent variable. I think we've said is compliance, and we've also, I think, said quite clearly that it's measured dichotomously. It is or it isn't. Right? And they say quite clearly in their coding criteria that partial credit is not granted, right? That you can't comply with some of the demands and be considered compliant. You either comply fully or you haven't, right? And so think about that in terms of like an area where another researcher might come along and say, I think you're using an axe where you should use a scalpel, right? I think that we should think about compliance in terms of no compliance, some compliance, full compliance, or something like that, right? So that would be a critique or a way of scrutinizing or building off of this study, right? Might be by measuring compliance in a more nuanced fashion. So these are the kinds of things that you can think about when you're considering a research design, right? What are alternative possibilities that might grant better explanation? Nonetheless, compliance here, they say very clearly, is full compliance or not. Very quickly, can somebody run through the independent variables? There are 3 of interest. And of course, we heard before, it has to do with nuclear possession, right? Shannon mentioned it's like, you know, who has the nuclear weapons? Connor?
It's whether there's a nuclear challenger, a nuclear target, or the interaction term of the two, which I didn't really understand what that means.
Great. So I'm going to show you that really quickly. Okay. So we have, let me move you all. We have our variables laid out here, right? All of them are dichotomous. Do you see why I assigned you this paper now for crosstabs? We use cross tabulation when we have a categorical independent variable and a categorical dependent variable. So they go on and use some other methods because they're doing multivariate analysis. But I think their research design sets them up really well, at least for a basic bivariate test via crosstabs. Categorical independent variable, categorical dependent variable. So does the challenger have nuclear weapons? Does the target have nuclear weapons? Do they both have nuclear weapons? That's what an interaction term is. And I'll tell you why it's an interaction, besides just the fact that it's do they both simultaneously. So I'll do this really quick. Might not be very pretty, okay, just as a heads up. But let's say here we have our unit of analysis, which would be the dyad and country A and country B. And then we have our dependent variable here. And we have our independent variable 1, independent variable 2, and independent variable 3. And this is all just, you know, other variables because I didn't space out my columns well. All right. So here we have the dyad. And we'll call it dyad number. So this would just be, you know, some number to represent each. I'm sorry, that's wrong. That's not the dyad number. Let me back up. This would be the militarized interstate dispute, and it would have some number assigned to it, just like a barcode, right? At the grocery store, it would have some number assigned to it. You would then have the challenger and the target. So let's just say country A, country B, right? And we'll do that all the way down. And at some point, right, we would get some other countries or dyads in the mix. You might have F and J, right, for a bunch of observations. And you might have, you know, P versus R, right, or C or something like that, right? P versus R. Maybe they have a few disputes as well, okay? So you can have multiple disputes amongst the same dyad. Good. So challenger, target. We have the dependent variable. The dependent variable, as we said before, is compliance, and that's 0 or 1. So we'll have no compliance for some and compliance for others, right? And then we have independent variable 1, independent variable 2, and independent variable 3 that we set above. Independent variable 1 is, does the challenger, right, A, have nuclear weapons? So sometimes they do, sometimes they don't. Okay. We then have the target. Sometimes they have nuclear weapons, sometimes they don't. Okay. Last is the interaction term. Do they both have nuclear weapons? What you could do, of course, let's pretend that you don't have independent variable 3 in the data set, right? You could go through and simply say, well, does this one and this one? If so, it's a 0. Or, I'm sorry, if neither of them do, it's a 0. This one, right, the challenger does and the target does, and so that would be a 1. But instead of doing it manually, right, the quick way, and the reason we call it an interaction term, is we simply multiply these. If there's a 0 in either column, then the answer is 0, right? Because 0 times anything is 0. So if there's a 0 in any column, it's a 0. So I'm just looking for zeros. 0, 0. And if there is simultaneously a 1 for both the challenger and the target, then it's a 1. To indicate that they both have nuclear weapons. So then ultimately what crosstabs is going to do for us is to see if there's a systematic association between having nuclear weapons as a challenger and compliance, having nuclear weapons as a target and compliance, and third, simultaneously having nuclear weapons by both actors and having compliance. Now, sometimes you're going to have compliance when you don't have nuclear challengers, or you don't have nuclear targets, or neither is nuclear. Sometimes you won't have compliance when one is a nuclear power, right? But the question is, generally speaking, over the long run, as a kind of pattern or trend that we typically see with a small degree of uncertainty that would give us a p-value below 0.05, can we say that in general, any of these hypotheses are true, right? When you have nuclear weapons as a challenger, you're more likely to obtain compliance. If generally speaking, that's the case, right? Not just more often than not, but more often than not with a small amount of uncertainty, then you'll get a p-value less than 0.05. Okay. Now, if you'd like, I can talk to you more about the crosstabs equation that was in the lecture. But before I do that, I'd like to give people just, well, first of all, do you have any questions about what I just discussed and what you all, frankly, brought to the table with the Sexer and Furman article? Why that represents cross-tabulation, why those variables we would call dichotomous, anything else about the study design? And if not, I'd like to give you 5 minutes or so just to kind of like take a breath. We'll come back at 7:31 and we will take any questions you have at all about problem set 1 or about content from class 4 and 5. Okay, which includes statistical inference and cross tabulation. Is that good? Fantastic. See you in a few minutes. Thank you so much for reminding me of that. So we missed some things, unfortunately, in the recording, but hopefully you've jotted them down in your notes. It's just since we've come back from our few minutes break and talked about the problem set Q&A. So thank you. And please, if anybody recognizes that going forward, as Jacob just did, let me know that, because I do intend to have these things in the recording. I just had a thought about something I wanted to show you. Oh, so in the discussion forum, somebody asked about do files. So let me just do a couple of other things here. Let's say we mess up. Let me just, okay, so that's an error. And then maybe we can do, tab region. I'm just going to do a few additional things. Summarize year. Let me show you a command I don't know that you know yet while I'm just creating random commands. Tabstat is a great command for getting descriptive statistics. I don't know if I've shown this to you yet anywhere. Maybe in one of the lectures. But Tabstat gets you descriptive statistics, but only the ones you want, right? Like, summarize here gives you the number of observations, the mean, the standard deviation, the minimum, and the maximum. Or, right, you can add detail, right? And it gives you a bunch more that you don't want.
You're not sure. You're not
gotcha.
sure.
Mm-hmm. Right, so you have these statistics that you automatically get. Or, if you do code book to get some statistics, right, it gives you some, right, the mean, standard deviation, certain percentiles, etc. But Tabstat is cool because if you do help Tabstat, you'll see that it's just the command Tabstat plus some variables, one or more variables, followed by options. And most of the action for Tabstat is in this option here, statistics. And so you do the statistics option, which is just abbreviated as S, if you want to use the abbreviations, right? So statistics or S. And then in parentheses, you put names of statistics that you want, right? So I just clicked stat name, and down here you get a whole bunch of names of statistics that you can call in that option. So let's say I want for, what's an interesting variable? Let's do rural population percentage. Let's do another one too. I think there's one on telephones per 100 people. Okay, so those are the two variables we want statistics for. We can then just do comma S, and then in parentheses, put the statistics we want. So let's say we want mean, variance, standard deviation, min, max, hit enter. And for those two variables, we get the mean, variance, standard deviation, minimum, and maximum. Nothing more, nothing less, right? It's just what we ask for. This is really nice when, let's do that again. For those of you who have already started working on the problem set, which I recommend for sure, let's say you want the quartiles and the interquartile range, right? Q and IQR. So now you get the quartiles, 25, 50, 75, as well as the interquartile range. It will do the subtraction for you, 73 minus 32, right? 40.7. Or 19.06 minus 0.6626 equals 18.40. So that's a really quick way to get the statistics you want. So that's my main descriptive statistics command, is to use Tabstat. It also then gives you a nice little table that you can go and replicate in Microsoft Word or whatever. So now this is what I wanted to tell you about. When it comes to the do files, I want an appendix at the end of your problem set with your program code, your do file. I don't want everything you've ever tried. I simply want the stuff that got you to the correct answer or the answer that you ultimately obtained. This is important though. If you don't get to an answer, right? Let's say you just didn't get to a final answer. You had errors, you tried a bunch of things, but you just didn't get an answer. You couldn't produce the table or the histogram or do the hypothesis test or whatever. At least show me a thing or two that you tried there, even if it failed. Because then I can at least grant some partial credit, number one. And number two, I can see what did you do and where did you go wrong. So number one, don't show me everything that you tried that didn't work, followed by the stuff that you did try that did work that got you the answer. Just show me the stuff that worked that got you the answer. Unless you didn't get an answer, right? That you didn't get to an outcome. In that case, show me something that you did try or a couple or few things that you did try, okay? Any questions about that? Okay, so that's just a general principle. Now, you know that you are generally supposed to work in a do file. Where is the do file? Here, which is just like a blank Word, text document. By the way, I didn't mention this to my other session yesterday, but in the data folder, there is something called do file template. And it just has in the top a section where you can kind of title your do file, put a date on it, say what data set it's associated with, right? What data set does it work with? When was it last modified? You don't have to use it, so don't feel compelled. But I use it because it helps keep me organized when I'm working on a project that has a do file that goes through lots and lots of iterations. It kind of tells me what's the name of the file, what data set is it associated with, when did I create this do file, when did I last modify it, etc. So it's just notes at the top. But what you know is that, right, you can type directly in here, like tabulate physint democracy, like we did before. And if you highlight this and click execute, it will run over here, right? Because they communicate with each other. So you know that about do files already. So you could do everything in the do file and simply run it. And it ends up showing up here as just this code, right? It ran your do file or some line from your do file. Alternatively, I know a lot of you like to work like I do in class in this command line down here. And when you type a command, it shows up in your history over here on the left. So if you do it that way, right, the easiest way to get that from your history into the do file is to copy and paste. So I just want to make sure you know you can do that. You can highlight things individually or completely. So if you click on the top, hold shift and click on the bottom, it'll highlight everything. But as we said before, a lot of times we don't want everything. We want the stuff that worked and the stuff that got you an answer, right? So stuff that was an error you don't want, and stuff that was you calling a help file or something we don't want, right? We just want the stuff that gets you the answers. So we would take out certain things. You can do that by holding the control key and just clicking individual things. So that failed. This is just a help, right? This is just a call to a do file. So I'm holding control and clicking those, and they will no longer be highlighted. Once I've done that, I can now copy with edit, copy, or control C, as you know. I can then go into my do file and do control V or edit, paste. So now I have my commands in my do file. I'll take questions in just a second if you have any, but the last thing to know is that I don't want to see a do file like this, right? it's good practice in quantitative analysis for the purpose of replication, right? So other people can see what you've done, to organize your do file, to give some indication of what's going on in different places. Just like I did if you look at my do files for your tutorial, right? I break them out into different exercises and different things, and I tell you what's happening. So I don't need you to do that extensively here, right? But you know, based on starting with Stata tutorial number 3, how to add notes, right? The easiest type of note is just with an asterisk at the beginning of the line. And so you might do something like load data set. You can come down here and you could do question 1, right? Come down here, question 2. Maybe question 2 has multiple components, right? So this would be A. Maybe this is for BI. This is for BII, right? This is for BIII, right? So you can organize it how you like, but make sure that it's clear to your audience, which in this case is generally me, what's happening where. Because I want to be able to see correspondence between your do file and your report, so I don't have to kind of try to decipher what you're doing for which question and that kind of thing. Great. Okay, other questions? We have just a few minutes. Of course, I will stick around after class for anybody who wants to chat a little bit more. But what other questions do you have about the problem set? I know we only have a few minutes, but anything else that just comes to mind? Okay, so let me say one last thing. And then, no, two last things. They're super quick. Number one, you currently, I said before, I will never ask you a question that I didn't cover, right? In a tutorial, in a problem, in a practice problem, in a class lecture. Well, I screwed that up, and number 7 asks you about something that I haven't taught you yet. It's about correlation and covariance. I originally had those included as a kind of add-on to descriptive statistics. We know descriptive statistics are generally about one variable, right? Mean, median, standard deviation, variance, etc. But there's also something called bivariate descriptive statistics. Before we test a hypothesis, we could just describe two variables and their association. Covariance and correlation is one of those. And I realized that I was giving you a lot of content and that it was the start of the term and there was a lot of just uptake going on. And so I cut that off. But I kept the question in the problem set by mistake. And so what I'm going to do, somebody brought this to my attention just last night. I'm going to send an email message out after this class. I'm literally making a decision right now. And I'm going to cut question 7. Okay, so you can just completely ignore question 7. It also asks you to provide a scatter plot. You no longer have to provide a scatter plot. It asks you to interpret the correlation, the covariance, and the scatter plot. You don't have to do that either. That's part C. So full number 7, A, B, C, I think there's just 3 parts, cancel. Okay, and I'll send that out in an email. And then the last thing And I apologize for making these kinds of revisions. Just, it's a lot of content for you. Trust me, it's a lot on my end also. Those of you who have office hours scheduled with me tomorrow who are currently present, which I believe includes Chanel and Sally, and is there anybody else? Is Mustafa here? No, he was last night. So just the two of you, Chanel and Sally, since you have office hours with me, can you stick around for just a minute after class? Okay, thanks. Something came up tomorrow and I'm just having some scheduling issues, so I just want to chat with you briefly. Okay, great. I think that's it. Sorry for the extra minute, but that's better than I've been in the past, so progress. I'm happy to stick around though afterwards and chat with anybody who wants to stay. Otherwise, have a great rest of the week. See you next time. Take care.
I have a quick question.
Please.
So